My name is Gedanken. I am from Bar-Ilan University. I am the coordinator of a JPI AMR project whose title is Investigating the Mechanism of Eradication of Multi-Drug Resistant Bacteria by using inorganic mixed metal oxide or organic antibiotics and protein-based nanoparticles. This is a project. The participants are coming from 3 countries, as you see here: Bar-Ilan University in Israel, University of British Columbia in Canada, and University Politecnica Catalunya from Spain. These are the 3 universities participating in this project.
Before telling you about our project, I would like actually to give you a short introduction about antibiotics and antibiotic resistance. And I would like to start with taking you back to really an important date in the history of antibiotics, and that is September 28, 1928. And we're going back to the laboratory of Alexander Fleming. Fleming was just returning from his vacation, summer vacation, and when he walked into the lab, he saw that he forgot by mistake a few plates that were growing on his bench, plates containing a bacterial pathogen he was studying called Staphylococcus aureus. And just before he was going to throw them out, he took an extra look, and this is what he saw. So what he saw was his bacteria growing, but in addition, there was a contamination on the plate. And what was interesting is that the contamination, which was a fungus, inhibited the growth, had a clearing zone that inhibited the growth of the bacteria on the plate. And this is what he wrote about this moment. When I woke up just after dawn on September 28, 1928, I certainly did not plan to revolutionize all medicine by discovering the world's first antibiotic or bacteria killer. But I guess that was exactly what I did. And indeed, this is a remarkable finding. So together, Florey, Chen, and Fleming isolated the antibiotic and made it into a therapeutic agent that could treat millions of people. And you have to imagine that at the time, people were dying from simple infections. So the average lifespan was 45. And by finding this remarkable drug, this had a huge impact on the lifespan as we know it today, which is about 79, 80 for people living. Now, this really opened a golden era in antibiotic resistance because suddenly researchers understood that antibiotics are out there in the environment produced by microorganisms such as fungi in order to outcompete other microorganisms. And people like Waxman, who got the Nobel Prize, started finding new antibiotics. And this was a really golden era where most of the antibiotics that we use today were discovered. In fact, the situation was so good is that the Surgeon General of the United States in the middle of the 60s came with the statement that we can close the book on infectious diseases and can move on into new problems, medical problems such as heart attack, stroke, diabetes, etc. But bacteria were fighting back. And in fact, using mutations, using horizontal gene transfer, and of course, hard selection of antibiotics, they were finding new means of avoiding or overcoming the antibiotic agents. And in fact, we had the sign on the wall. Because even before we started to commercially use penicillin, which was the first antibiotic, we already knew, scientists already knew, that there's genes that can give resistance. And in the last 30, 40 years, bacteria slowly but very forcefully found resistance. And today, we're hitting a situation where we're approaching the post-antibiotic era. And in fact, there have been 2 crucial reports about this issue. One coming from the CDC in the United States and one by the World Health Organization that were stating the urgent need that we are in this case of multi-drug resistant and extremely drug resistance in bacteria. And before going on, I would just like to explain you what is this resistance. So there's a few mechanisms by which bacteria overcome antibiotic. The first is that they secrete enzymes that can either degrade or modify the antibiotic, and by this way make it non-functional. Another way is just to block its entrance into the cells. And the third way is to actually, even if the antibiotic gets in, pump it out using special pumps outside of the cell so it will not harm any intracellular activity of the bacteria. Another option is to change the target. For example, ribosomes. Some of the antibiotics inhibit protein synthesis, which is carried out by the ribosome in bacteria. By changing the ribosome in such a way that it is still active and able to efficiently make proteins, but yet not bind the antibiotic, the bacteria are becoming resistant. The last mode of resistance is a specialized mode of growth that bacteria can take, which is called biofilm. And biofilm is very special. It's a situation in which the bacteria live the free-living planktonic growth and actually aggregate together into something that looks like a multicellular organism, in which basically they secrete a specialized polymer that binds them together, as you can see in the electron micrograph image below. And what's important about this state is that this state is a way of bacteria to become resistant against harsh conditions. This could be UV, heat, and also antimicrobial activity. And how are biofilms formed? It happens very quickly. So bacteria, which are about a micron in size, basically can bind a surface within minutes, and then in the beginning state, the binding is reversible. So bacteria will move on the surface, but after a few minutes to a few hours, the bacteria will become irreversibly attached. They will start multiplying, form microcolonies, secrete the matrix, and in a few days you will get a biofilm that is fully mature and growing. And this biofilm can disperse free-living bacteria that can inoculate new niches. The next movie shows you a biofilm formed in 24 hours. So the green dots that are moving on the surface are actually bacteria. And you can see some of them actually running on the surface. And after a few minutes, and we can actually track that, we see that the bacteria slow down and make a biofilm. And if you can imagine that something like this is happening on your heart or on your joints, that's a problem. And the main issue about biofilm formation is that once biofilm are formed, they are highly resistant. So they're resistant to disinfection, they're resistant to antimicrobial therapy, and they're resistant to the immune system. And because of that, biofilms have become probably the #1 cause of infection. The NIH estimates that 65% of the hard-to-treat infections in hospitals are caused by bacteria that are in a biofilm form mode of growth. All the chronic bacterial infection, chronic urine tract infection, chronic lung infection, all of those, the chronic is because the biofilm are formed and the immune system and our antibiotics are not working well on it. So we're having a problem. We are running out of antibiotics, and this is the heart of this consortium. Basically, in the last 20-25 years, we're seeing a slowly but gradually decrease in the number of new antibiotics that are out in the market. So we urgently need new solutions and new antibiotics that can fight these bacterial infections. And our consortium would like to utilize nanotechnology to offer a solution. Nanotechnology is the manipulation of matter on the atomic scale. A nanometer is 1 millionth of a millimeter. And you think about nanotechnology, it's basically like playing with Lego. We take atoms and, like Lego blocks, build molecules. And what's interesting about nanotechnology is once you start playing on the atomic level, you start getting new physical-chemical properties. One of them is enhanced or new antimicrobial activity, and this is exactly what we would like to utilize in our project. So basically, what we are offering and trying to develop here is a nano-based antimicrobial toolkit. We have 3 innovative projects, each attacking the question from a different molecule. So one will use novel metal oxide, which are highly potent antimicrobial agents, but making nanoparticles out of them will make them even more active. The other one is taking antibiotics, commercially available antibiotics, the ones that people have been using and the ones that are losing their activity against bacteria. And what we're offering is to make nanoparticles out of them and restoring their activity. The last one is taking proteins and making them nanoparticle spheres, and basically making a cargo that will take the antimicrobial agents at higher payloads and will also damage the cell and have antibiotic activity. The projects bring together a vast and very multidisciplinary group from Israel, Spain, and Canada. Each group has a different role here. The Israeli group and the group from Spain are focused on making the nanoparticles. All three groups are studying their antimicrobial activity, especially against multi-drug resistance. And the group in Canada brings in the information to begin and address the mechanism of action and also the pharmacokinetics of these molecules. At the heart of our technology is a very specialized mode of synthesis called sonochemistry. And to explain this methodology, I would like to invite Professor Aaron Gedanken from Bar-Ilan University.
Well, this project, or at least the synthesis of the materials in this project, by and large, are based on sonochemistry. Sonochemistry is a field of research in which, by passing ultrasonic radiation through a liquid, you are causing the liquid to undergo some chemical reaction. Sonochemistry, chemistry done by sono. And the question is, what is happening and why is it so important to the preparation of all the materials that will be mentioned later? Because when this ultrasound goes through the liquid, what is happening is bubbles are created in the liquid. And the bubbles grow, and as you see in the slide, they collapse. Upon their collapse, there is a dramatic increase in the temperature as well as the pressure. The temperature is reaching 5,000 degrees Kelvin or very high pressures. And under these extreme conditions, chemical bonds are broken and reactions are taking place. Chemistry is going on. Now, in this project, we are making some special, or we are utilizing a special phenomena that is involved with the application of sonochemistry. When the bubble collapses, the bubbles that I described before, when this bubble is collapsing near a solid surface, and the solid surface can be a piece of textile, piece of glass, a plate of glass, can be a 2 millimeter bead of a polymer. These are all solid surfaces. When the bubble collapses near a solid surface, there is an after effect. And this after effect is involved with some microjets that are moving very fast. And they are taking nanoparticles, throwing it directly onto the solid surface, embedding them in the surface in such a way that it's very difficult to remove them. They are staying there well embedded in the solid surface. So this is a deposition, a coating technique that in certain cases unparalleled. There is no something near it. Now, along the years, we have shown that we have two modes basically of deposition. The first one is called in situ, and it means that we are making, using the sonochemistry reaction, we are making the nanoparticles and throwing them onto the surface. The other one is called throwing stones. In this case, let's say that I don't know how to make the nanoparticles. I don't have a formula, a reaction that would prepare the nanomaterials. So in this case, I'm suggesting go and buy it from a commercial company and use the ultrasonic waves to throw stones at the surface. So these are the two techniques that I'm talking about. As you will see, in our case, we will use the two of them. With the inorganic materials, we are using the in situ. Namely, we are making some nanoparticles and throwing them onto surfaces. In other cases, we are using the throwing stones. Now, what is important is the capabilities that we have. You see in the middle of the picture, down there, we have a machine, a small machine. And in a movie you see a recent version of this machine that can coat roll to roll, namely some polymer, textile, whatever you want. If it's a continuous running through the machine, there are sono-chemical reactions that will deposit the desired nanoparticles onto the textile or onto the polymer, or even if the metal is very thin and can be rolled on a metal. This can be done in our machine. Now we are starting with the metal oxide. And first we are demonstrating what is the reaction that we are doing or carrying out in order to prepare, let's say in this case, zinc oxide and copper oxide. Both are antibacterial material, especially in the nano size. So as you see, we are taking zinc ions or copper ions, we are hydrolyzing them, and zinc oxide or copper oxide are being produced in nano size and deposited on the substrate. So this is regular metal oxide. Now, in the case of most interest to us is a new material that we have developed and suggested to extend the development of this material, and they are called mixed metal oxide. As you see here, copper 0.89, zinc 0.11 oxide is a material that has a capability to kill bacteria 10,000 times better than either zinc oxide or copper oxide. Very promising material. And for example, we want to synthesize in parallel a new one, copper magnesium oxide. And this involves, in the case here, the most promising material to kill resistant bacteria. And in this slide, you see 1, 2, 3, 4, 5, 6 different resistant bacteria that were killed by copper oxide or zinc oxide, which means that the probability that the new material will do the job is even higher, because it shows, and through the mechanisms that we are familiar and know, they are very promising to do a better job related to resistant bacteria. What is important is what is mentioned here in the slide, that once we deposit it on a surface, this mixed or pure metal oxide, when we deposit them, there are no leaching. These coated surfaces, let's say in the case of textile, were washed 65 times in a hospital washing machine. Hospital washing machine means 75 or 92 degrees centigrade. And after this long process, the nanoparticles were still on the textile and were showing very, very good killing of bacteria. What can be leached is the ions, namely copper ion and zinc ions. First of all, let me remind you that every morning when you eat cereal, you have zinc ions in your cereal, which is not bad. Secondly, the amount is dependent on a chemical equilibrium constant called KSP and this equilibrium constant is very small, so the number of ions is very, very small. Here we are showing the formation or fabrication of the mixed metal oxide. It requires that you weld at one time source of zinc ions and copper ions, and you do the hydrolysis that I showed you before, namely hydrolyzing simultaneously the two ions, forming this mixed oxide that I mentioned before. And how do we know that it's indeed mixed? This is dependent on shifts in the XRD, because here we are demonstrating the XRD of zinc oxide and copper oxide, and when you look at the position of the peaks, you will see that when we compare them to copper oxide, it's a little bit shifted. And this shift means that we indeed perturb the unit cell of the copper oxide by introducing zinc ions into it. And as I mentioned before, the activity is activity as far as killing bacteria is dramatically increased.
Okay. So our second approach is actually again utilizing sonochemistry. But this time, instead of using inorganic molecules, we're going to use organic molecules, and specifically antibiotics. So basically our idea is as follows. We're going to take antibiotics, commercial ones, and apply sonochemistry. And we know, and we'll show you in a second how it looks, that this process makes nanoparticles of antibiotics. And in fact, we can visualize these nano antibiotics on graphene oxide sheets. Now, why is this important? Because we hypothesize, and I will show you in a minute that this is actually the case, is that by making nano antibiotics, we can restore the antibacterial activity against antibiotic-resistant bacteria. So look at this figure. Here we compare the antibiotic of tetracycline, a commercial antibiotic, and a nanoparticle TET, which is marked here with GO TET. And you can see that we can restore the activity against a multi-drug resistant bacteria. So think about this idea. Basically, we can take any commercial antibiotic, all the antibiotics that stopped working years ago, apply a simple sonication process, and restore the antimicrobial activity. And we believe that this approach may make a really huge revolution and bring back to life all the antibiotics that have not worked. We further tested these compounds on a range of antibiotic-resistant pathogens that are common in hospitals. And as you can see, these nanoparticles of both tetracycline and ampicillin are very active. And during the course of the project, we're going to continue and develop other antibiotics with different activities and continue testing them on multi-drug and extremely drug-resistant bacteria. Our third approach is to use nanosphere for the prevention of bacterial infection and biofilm formation. This work is headed by Professor Tzanov from UPC in Spain. And the overall idea is to take proteins and basically make a nanosphere that will contain antimicrobial agents such as antibiotics, antimicrobial biopolymers, and anti-quorum sensing proteins. And the idea again is to use sonochemistry in order to make the nanosphere and cage in the antimicrobial agent. Now the strategy and the rationale around this idea is that the nanospheres by themselves will interact with the bacterial membrane, disrupting it. And in addition will bring a high payload of the antimicrobial agent. And Professor Tzanov is actually utilizing a wide range of techniques to study and understand this antimicrobial activity of these novel agents. And he has recently obtained very promising results during the first few months of the project. So what you can actually see here is how nanospheres of penicillin actually are more active than the penicillin solution, the pristine penicillin solution, the same antibiotic that Fleming discovered over almost 90 years ago. And you can clearly see that once we use the nanosphere, the nanopenicillin, the activity is much higher. In fact, Professor Tsanov went another step ahead and actually tested the activity against biofilms. And here, I remind you that biofilms are extremely resistant to antimicrobial therapy. And he used 2 strains to study it. 2 bacterial pathogens that often form biofilms, E. coli and Pseudomonas aeruginosa. And you can see very nicely that again, if he uses the nanosphere, the activity is much higher. And in red, what you see in the images are dead bacteria. So you can see that when we use the pristine solution of 2 antibiotics, in this case penicillin and vancomycin, we see that the solution itself is green. But once we use the bacteria, they are alive. But once we use the nanosphere protocol and agent, we're basically getting a lot of killing of the resistant bacteria. So this looks very promising. To summarize our talk, basically our consortium is focused at bringing and developing a nano-based technology of various antimicrobial agents that will be effective against multi-drug and even extremely drug-resistant bacteria. And hopefully our new materials, as well as our nanofabrication of commercially available antibiotics, will provide solution to this growing problem. So finally, none of what we've shown you today could have happened without the generous support of the Joint Programming Initiative on Antimicrobial Resistance and the funding agencies from Israel, Canada, and Spain. And the whole consortium would like to thank them for their generous contribution.
The consortium is built of 5 research groups, 2 from Israel, 2 from Canada, and 1 from Spain. The Israeli group comes from Bar-Ilan University, is headed by me. I am the coordinator of the project. A microbiologist, Professor Banin. Dr. Ilana Perlstein is responsible for all the experiment done with ultrasonic waves, and a PhD student, Anjani, is involved as well. From UPC, the head of the group is Professor Tsanko Tsanov, and under him there are 2 PhD students and 1 postdoc. The group from UBC is composed of 2 professors. Professor Bach is basically the coordinator of the UBC group. He is a microbiologist. He is measuring all the antibacterial properties in UBC. Professor Hafeli, and a master student of Professor Bach. This is the composition of our consortium.